So we have looked at Way ANOVA, which has one quantitative response and one categorical predictor. We have looked at follow-up analyses for Way ANOVA, including Fisher's confidence intervals and Tukey's confidence intervals. What we're going to do now is section 14.3 in the book, which is Way ANOVA. Way ANOVA is a multivariate method, the same way multiple regression is a multivariate method. It's an extension of Way ANOVA, which allows us to analyze the relationship between a quantitative response and two categorical predictors. So the 2 in Way ANOVA refers to the number of categorical predictors, just as 1 in Way ANOVA refers to the number of categorical predictors. So the number of ways in ANOVA is the number of ways that we can classify our data, or the number of categorical predictors that we have. So we're going to revisit the beer goggles data. Before randomly assigning the participants to a specific amount of beer, the psychologists in that study first randomly sampled 24 male and 24 female participants. The two groups were randomly assigned to alcohol levels in a balanced manner. And I should say, these were self-identified male and female participants, so this was not an observational study, or this is not based on observed genders. The two groups of males and females were then randomly assigned to alcohol levels in a balanced manner, so that the male participants were balanced across the 3 levels of alcohol, and the females were also balanced across the 3 levels of alcohol. So there were an equal number of males in each of the 3 levels of alcohol, and there were an equal number of females in the 3 levels of alcohol. So the study design looked like this. We had a pool of participants, and they were observed, based on the reported gender, to be male or female. Then the males were randomly assigned to 0, 2, or 4 pints of alcohol. The female participants were then also randomly assigned to 0, 2, or 4 pints of alcohol. So gender was observed. We cannot assign gender to participants. The amount of alcohol was done through random assignment. So this was both an observational study because of the gender, but an experimental study because of the amount of alcohol. So we can draw causal conclusions based on the amount of alcohol, but we cannot draw causal conclusions based on gender. There are 3 hypotheses that we are interested in, and I'm going to write them over here. There are 2 hypotheses about the directly about the variables that we just identified, and these are called main effects hypotheses. The first one is going to be a main effect of gender. That is, on average, do males talk to people of different perceived attractiveness than do females? The second is going to be about the amount of alcohol. That is, does the amount of alcohol, 0, 2, or 4 pints, have an effect on the perceived attractiveness of that people talk to? So this is that beer goggles effect. But when we're talking about these main effects, we are ignoring or we're averaging over the other variable of interest. And we'll talk more about what a main effect means in a moment. So there are 2 hypotheses for main effects. There is one hypothesis about an interaction. We've learned about interaction before when we did multiple regression. The interaction here is the same idea. We have to look at the interaction between gender and alcohol. That is, oh my goodness, I can't spell alcohol. I have not been drinking any today. That is, is the effect of alcohol on perceived attractiveness the same for males as it is for females? So we might think of it this other way. Is the beer goggles effect for males the same as it is for females? Or we might think of it, is the effect of gender on perceived attractiveness constant across all amounts of alcohol? So we have 3 hypotheses that we're interested in: the effect of gender, the effect of alcohol, and then finally the effect of the interaction. So in a Way ANOVA, a null hypothesis for no main effect states that the population means are the same in each category of one factor when averaged over levels of the other factor. So there are two main effects that we're interested in, so we need to write out what that means. So, for example, no main effect of gender would be our first null hypothesis. That means that the mean, or the true mean attractiveness, is the same for males and females when averaged over all levels of alcohol. That is, if we disregard or regardless of the amount of alcohol they drink, when we think about males and females, they're going to talk to people of the same average attractiveness. Because there's another categorical explanatory variable, that means there's another main effect of interest. And so that means there's another null hypothesis. That would be no main effect of alcohol. How do you think that you would phrase this? Pause the video, write down a possibility, and then restart the video and see if you've written it the same way that I have. Okay. The null hypothesis, no main effect of alcohol, is the same thing as saying that the true mean of attractiveness is the same for all levels of alcohol when averaged over both genders, which is the same as all levels of gender. But because there are only two genders, we can say both. That's more specific. So if there is no main effect of alcohol on attractiveness, then that means the true mean of attractiveness is the same, but we're averaging over all genders. If there's no main effect of gender on attractiveness, that means the true mean attractiveness is the same for males and females when averaged over all levels of alcohol. In Way ANOVA, a null hypothesis for no interaction states that the changes, so remember, interaction is about the change in the effect. So the changes in the population means between categories for one factor are the same for all levels of the other factor. So this is about parallel lines, only now we're dealing with parallel line segments. So I'm going to scroll over here to give myself a little bit of space. So the null hypothesis, so no interaction between gender and alcohol. In this case, that means that the effect, or the true effect of alcohol on attractiveness is the same, right? The null hypothesis means equality, so the same, does not change, is the same at all levels, which is the same as both levels of gender for both genders. So that means when we look at the effect of alcohol, it's the same for males and females, which is how we thought about it before. So if there is no interaction, we're going to have the same change for alcohol when we go from 0 to 2 and 2 to 4 for males, and it's going to be the same change for females. So what might that look like if we have these null hypotheses? Well, if the null hypothesis is true, using the data that we have, then the effect of gender would be that that when we average over the levels of beer and just compare males to females, using the data that we have, then there would be no change. So there would be no main effect for gender, no main effect for gender. So when we average over beers, the change would be 0. So males and females would have the same average perceived attractiveness of 58.3. So this would be the first null hypothesis, no main effect of gender. So averaging over beer, males and females are going to have the same response. What if there's no main effect for beer. That means averaging over gender. So taking gender out of the equation, we're going to have the same average response for all three levels of beer. So that would be 38.9, 38.9, 38.9. On average, you're going to have the same perceived attractiveness regardless of the amount of beer you drink. So this would be no main effect for alcohol. I'm not sure why I have all these other plots. I only really need one more. If there were no interaction effect, we would see the same change in the mean response between males and females regardless of the level of beer. So we might see something like 60.2, 56.5, 60.2, 56.5, 60.2, 56.5. That is, if you have 0 pints of beer, when you compare females to males, we see the same average drop of about 4 points. If you have 2 pints of beer, we see the same average drop of 2 points. And the effect of 4 pints of beer, or the effect of gender when you have 4 pints of beer is the same drop of 4 points. We might instead, and now I'm remembering why I have these extra things, so this would be for no interaction. We might instead see something like this: 63.8, 63.8, 64.7, 64.7, 46.6, 46.6. And if we had data that looked like this, we could say, well, if you are female, so for a fixed level of gender, the change when you go from 0 to 2 pints is about 1 point, and the change from 2 to 4 pints is a drop of about 20 points. But if you're male, you see the exact same change. So when you hold a fixed level of one factor, in this case gender, the change in the other factor, beer, is the same. And so using our sample means, if there were no interaction, we would have the same average changes in the response for beer in this case when we look at either males or females. For this other plot, when we look at the change between females and males, when we look at 0, 2, and 4 pints, we're looking at the same change as well. So these are both two examples of how we might have no interaction. But what our actual data are is 60.3, 66.9, 62.5, 66.9, 57.5, and 35.6. Now, when we're thinking about this, at 0 pints, what is, if we had to eyeball this, what is the approximate mean response for people who have 0 pints of alcohol? We can estimate that to be about 63. And for people who have 2 pints of alcohol, we can estimate that to be maybe a little higher, maybe 64-ish. But for people who have 4 pints of alcohol, we can see that that is a much lower response. So that's going to be, maybe 40 something. So there does seem to be, when we average across the gender, so the average response, this was about 63, this is about 64, this is about 40, what did we say, 45-ish. So the mean response for 0, 2, and 4 pints is not the same. It's not what we might have seen just based on if there were no main effect of beer. But we had to average the males and females at each of the levels of beer to get that estimate of the main effect. So we do have some evidence that there is a main effect of beer. Let's do the same thing here. So what is the average response for females regardless of the amount of beer they had? So for all the people in this female group, the average is, somewhere around 60. So let's call that about 60. And the average for the male group, it looks a bit lower, so let's call that about, 50-ish. Again, just eyeballing it. So for the male and the female group, does the average response for the female group look to be about the same as the average response for the male group? Again, no. But to get to that average for the females and the average for the males, we had to average across the amount of beer that they had. That gives us the main effect. That comparison of these column means now gives us the estimate of the main effect for gender. Now, to get at the interaction effect, what we're going to do is we're going to look at each difference in the rows or the difference within each column. So within the rows, comparing the females to the males, here we see a change of about 6. For the 2-pint group, we see a change of about 4. Now, is 6 and 4 the same? No. Is it a big difference? Not really. So we see some evidence of a difference in effects when we go comparing males to females at 0 pints and 2 pints, but it's not that big of a difference. The lines would probably be pretty close to parallel, but we also have one more group, the 4-pint group, to compare. So we have a change of 6, we have a change of about 4, and then here we look at the change, and this change is in the opposite direction. This is a change of negative 12. Nope. 22. So now we're seeing not only do we have a much bigger effect, but it's an effect in the opposite direction. So the effect of alcohol, or the effect of gender changes depending on how much alcohol they had. When we compare males to females, usually for 0 and 2 pints, they're talking to people who are more attractive. But suddenly, when males are drinking 4 pints of alcohol, they're talking to people who are much less attractive on average than females. So now we've estimated our interaction effect. So how do we all do this? Well, we look at our separate effects tests. This is the test for the null hypothesis of no main effect for gender, or for alcohol. This is the test for the null hypothesis of no main effect for gender. And then we have our third test, and this is a test for the null hypothesis of no interaction effect between gender and alcohol. We interpret our F-test statistic and our p-values the exact same way. So this F-test statistic is saying we have got 20 times as much explained variability as we do unexplained variability when we use alcohol to predict attractiveness as when we leave everything else unexplained. But we do have gender and the interaction as part of our explained variability. When we use gender to predict, when we use this main effect, so when we average over beer and we compare the difference between genders, there's 2 times as much explained variability as there is unexplained variability. That's not a very big effect. And in fact, if there really is no difference between the genders when averaging over the amount of beer consumed, we're going to see an effect like this, or more extreme, about 16% of the time. It's not that unusual. In terms of the interaction, and this should come as no surprise because we even see a change in the sign, we have 11.9 times as much explained variability when we compare these different changes. We have 11.9 times as much explained variability as we do unexplained variability when we use this interaction effect. That is, the interaction explains 11.9 times as much explained variability as it does leave unexplained when we have these other 2 terms, beer and gender, in the model. We're going to see something like this less than 1/100% of the time. That's pretty unusual, and so we have strong evidence of both an interaction between beer and pints and of a main effect for pints. So where does all of this come from? We do this using an F-test. We test the collective effect of all of our explanatory variables at once, and that's done using an analysis of variance, our good friend ANOVA. This model contains 2 main effects. plus 1 interaction effect. The degrees of freedom are based on the total number of parameters in the model. In our case, there is, we can count up the number of means that we have, or we can think about the number of regression coefficients needed, and we'll see that in the next video. This model is the same as testing all of these effects simultaneously. So what we really want to do is we look at this first. So check the overall model first. The same way we would do in multiple regression, and the same way we would do in Way ANOVA. We check the ANOVA first and then look at the separate effects. If the overall analysis or if the overall model is not useful, then it would not make sense to look at whether an individual effect is useful. So we look at the overall model, and we can see that this overall model with 5 degrees of freedom is the same as checking each of the individual effects, which have a total of 5 degrees of freedom. So the overall model, there's strong evidence that at least one of those 2 main effects or the interaction is useful. So we come down and investigate which. Well, we've already seen there is strong evidence of the main effect for beer and the interaction effect for the interaction effect between gender and the amount of alcohol. What does this look like graphically? We can do this using profile plots. So we might call these profile plots. We can call them main or interaction as appropriate effects plots. Or we might call them means plots, because what is actually being plotted right here at each of these points are the group means. So for example, this point here at beer equals 0 is the mean response for everyone that drank 0 pints. That is the mean response for males and females, so everyone in the group, whether you're male or female, who had 0 pints. This response here is the mean in our sample for everyone who had 2 pints. And then down here is the mean response for everyone who had 4 pints. And what we're looking at in this plot is the profile of the effect. So here we see that on average, people who had 0 or 2 pints of beer had about the same mean response. So this line is roughly horizontal. But when they drank 4 pints of beer, the line, or the mean response, is quite a bit lower, so the line is decidedly not horizontal. So when we see a non-horizontal line, that's evidence of an effect. So horizontal line segments like this, or close to horizontal line segments, that's evidence of no main effect, because that means the means are all pretty similar. We do have to be mindful of the scale of the plot, however, because here we see that female versus male, this is not horizontal, but we can also see that the difference is only about 4 points. So this is a small effect. It looks almost as big as the effect plotted next to it, but this is on a much different scale. So this scale is 75 to 40, whereas this scale is 66 to 52. So be mindful of your scale on your axes. This is an effect of about 20 points. So watch your scales, don't be misled. If we were to plot this second plot on the same scale as on the main effects plot for the beer, we would see hardly any difference at all. Finally, this last plot is our interaction plot. It helps illustrate the idea of interaction. So with regression, what we were looking for evidence of an interaction were lines that were not parallel. We're looking for the same thing here. In this case, because the change from 2 to 4 pints is not the same as a change from 2 to 4 pints for males and females because those line segments are not parallel. So this change here is not the same as this change here. We have evidence of an interaction. So we're looking at each line segment. So if the line segments are not parallel, that's evidence of an interaction. And we can see here that these two first line segments, they're not perfectly parallel, but they're pretty close. And this is close because of the natural variability in our samples. We don't need our samples to be perfectly parallel. Here, I would say that that's a pretty small effect. The difference in those two effects are pretty small. It's pretty close to zero, so I wouldn't worry about that. So if I had line segments that looked something like this, and then this next one was like this, and then like that, so not perfectly parallel, but pretty close, I would still say there's weak evidence of an interaction there. But here, there's very strong evidence of an interaction because of what is going on between 2 and 4 pints. That change between 2 and 4 pints tells me that males and females are reacting very differently, and therefore we have an interaction. The effect of alcohol is not the same on males and females, or at least we have strong evidence that the effect of alcohol is not the same for males and females. And that's consistent with what we see in our test here.